So I've had a lot of students come in recently for a urine physiology lab in the biology department. A lot of people, the underlying lab is not super confusing, but the thing that tends to confuse them is the chemistry that's associated with it. Um, I know that a lot of the stuff I'm going to go over is very basic when it comes to chemistry, but a lot of the anatomy and physiology students that I see on a regular basis for tutoring come in and they lack a strong chemistry basis or background, either because the underlying topic scares them or the math associated with it scares them, or they just haven't had it in a really long time. So, not to worry, we can go over just, the basic details of all this in enough depth to give you an understanding of how this lab is supposed to work. If you are a chemistry or biochem major or anything like that, keep in mind that a lot of the stuff I'm going to say is very superficial. So if you're looking at more complicated bonding, I've got other videos that are out there. They're not on YouTube, but they're on other sites. But for general anatomy and physiology, this is the level of chemistry that I'm expecting people to understand. To start out with, before we can even get into how to use the periodic table or anything like that, you need to understand a few basic terms. The first one is an atom. An atom is the smallest unit of a particular element that maintains the properties of that particular element. What that means is if you have, for example, water, you can break water into smaller pieces. So a molecule of water breaks into atoms of hydrogen and oxygen. But you can't break the atoms of hydrogen and oxygen into any smaller pieces without them changing the properties that are associated with them. So when we look up the basic structure of an atom, they look very similar. And a lot of the time you see a three-dimensional representation, or you see a two-dimensional representation, because we have a really difficult time drawing out the three-dimensional representation. And to be honest, the structure that we look at when we look at it on paper is not really accurate as to what it looks like in real life. But it gives us an idea of what the structure would be, and then the energy levels that are associated with it. So whenever you look in a biology textbook or even an entry-level chemistry textbook, you usually find a picture that looks something like this. And when you find this picture, you'll notice that there are several different areas that are in the atomic drawing. The first one is the center area right here, and I'll just kind of shade this in a little bit. This area in the center is known as the nucleus. The nucleus contains two different subatomic particles. The first particle is a proton, and the second particle is a neutron. The proton and the neutron make up the vast majority of the mass of the atom. And the specific mass is actually really easy to remember. A proton weighs 1 AMU, and an AMU is a very, very, very small unit of measurement for mass, and a neutron weighs 1 AMU. But a lot of people have heard that there's a third subatomic particle, which there is, and that's an electron. And an electron is present surrounding the nucleus. And the electrons in the two-dimensional representation, it looks like they flow in circles around the nucleus. But in reality, what actually happens is you have electrons, they form a sphere around the nucleus. So if you have the nucleus here, the electrons will not orbit, but they will rotate around the nucleus to form different levels of spheres around the nucleus. You'll hear people say energy levels. On a two-dimensional representation, the energy levels are distances from the nucleus. So this would be one energy level, this is another one, this is another one, this is another one. How it's particularly relevant is at any one time, and there's some upper-level chemistry and some upper-level physics that kind of argues with this, but for the purposes of biology it works. At any one time, electrons can only be a certain distance from the nucleus. So we separate those out in energy levels. And it's very, very easy to understand when you look at the periodic table how many electrons can be in each energy level at any one time. The rule that we use for this is called the octet rule. What that means is in the first shell of electrons, you can have up to two electrons. In the second shell of electrons, you can have up to 1, 2, 3, 4, 5, 6, 7, 8. In the third shell, you can also have 8. 1, 2, 3, 4, 5, 6, 7, 8. The good news is, for the purposes of biology, we will rarely, if ever, get above the third shell. So when we look, just like we said, we have the electrons, but the mass of the electrons are much, much, much smaller than the mass of the proton and the neutron. So specifically, the mass of an electron is about 1/1800th of an AMU. How this is particularly relevant to all of us is when we're counting up the mass of an atom. In physics, or especially particularly in nuclear physics, you have to count every single particle. But for the purposes of biology, because the mass of an electron is so small, if you can take into account the mass of a proton and the mass of a neutron, you're pretty adequate when it comes to, calculating molarity and molalities. And when we get into osmoles, electrons rarely come into play. The thing that electrons are really important for is with molecular bonding, because when we look at this particular drawing, we can see that this has 1, 2, 3 different levels of electrons, 3 different shells of electrons. But the only shell of electrons that comes into play for bonding is the outermost shell. So the outermost shell is referred to as the valence shell of electrons. So in this particular case, the valence shell of electrons is full. And if you have a valence shell of electrons that is full, that's usually an element that's called a noble gas. And when we get to the periodic table, we'll look and see where the noble gases are located. But you'll notice that whenever we look at the number of electrons versus the number of protons versus the number of neutrons, there's always an association to be made. And that's because whenever we look at the periodic table, we'll notice that each element as it sits on the periodic table is neutrally charged. Now, we haven't mentioned anything about charge yet, but a lot of the stuff you already know from 8th grade, just basic earth science. So effectively how it works is protons maintain a +1 charge. They have a positive charge. Electrons maintain a -1 charge. This is confusing for people on a certain level because electrons are so much smaller, so they would think that the charge of an electron would be very, very small. But it's not the case. Electrons are just as negative as protons are positive. Now, neutrons are very, very simple. Neutrons do not have a charge. So whenever we're looking at the charge of an atom, the neutrons don't bear into it at all. The reason the neutrons are present inside the nucleus is because when you begin to have bigger nuclei, you need to have something that spreads the protons apart, because each proton is positively charged. And you have to overcome a large amount of force to stuff those protons together in one space. The reason this becomes an issue, and the Paula Abdul song from the 1980s kind of spells this out, opposites attract, but in this particular case, the like charges repel. So if you have two positive charges, they will repel each other, but if you have a positive and a negative charge, they will attract each other. This is particularly important when we start looking at different types of bonding, because we'll look at covalent versus ionic bonding, and that really comes into play when you look at what something's going to do whenever you disassociate it into water. And there's a really complicated branch of chemistry that has to do with that. But for the purposes of us, we're just going to get into some of the more basic, the common ones that you tend to see in your body. So let me clear this all out. So I want to give you guys some examples. And a couple of the examples I'll give you, and I'm going to open up a periodic table here. And when you look at the periodic table, this tends to confuse a lot of people because there's a lot of letters and there's a lot of numbers. But hopefully we can, kind of dispel some of the, you know, scary type stuff that was instituted in chem class, back, 20 years ago. So, whenever you look at the periodic table is broken down into rows, across, and columns up and down. So with the rows and columns that you have across and up and down, what happens is these begin to organize the number of electrons that you have, the number of shells, and the number of electrons in the outsidemost shell. So let's look for just a minute, and we'll see that hydrogen has a number that is right here. That number is called its atomic number. The atomic number represents the number of protons in the nucleus. But coincidentally, because the hydrogen as it sits is neutrally charged, you have one positive charge that's being produced by the one proton that's present. But since it's neutrally charged, you also have to have one negative charge to offset that to make it so hydrogen is neutral. So the atomic number is the number of protons, but it's also the number of electrons when it's neutrally charged. The other number that you see and that we will use fairly commonly is this number down here at the bottom. It's 1.008. 1.008 is the atomic mass, or the atomic weight, and the atomic mass is the mass of the element as a whole, and it takes into account the protons, neutrons, and electrons. You'll notice that there are times when the atomic weights look a little weird. For example, with carbon, 12.011, or oxygen, 15.999. The reason that these look a little weird is because the atomic masses that you see on the periodic table are the average concentration of everything you'll find on planet Earth. So you have different isotopes and different ions of each particular element, and we'll get into what an ion is a little bit later, but you have different structures or different forms of it. And the atomic mass in the periodic table just gives you an average of each of the masses of all the different elements. So effectively, when you look at this, let me get rid of this pen, and I'll go back to red. So as you go back to the periodic table, the row that you're looking at on the periodic table, the row across is the number of electron shells that you're looking at. So for example, hydrogen has one electron shell, and because it's in the first column, there is one electron in that shell. Helium has one electron shell, and there are two, because it's the second electron in that row, or second element in that row. So helium has one electron shell, and the outermost electron has two in it. Lithium, because it's in the second row, has two electron shells, and because it's the first one in the row, it has one electron in it. Beryllium has two electron shells, and because it's the second one in the row, has two in it. Boron, two shells, 3 electrons in it. Carbon, 2 shells, 4 electrons in it. You just progress across. The question that comes in, and this goes back to the atomic structure that we drew before, what's the maximum number? Well, if you ever forget on an exam, you can just count across. This particular central area is the rare earths, and for the purposes of most general biology and anatomy and physiology classes, we don't really get into those. So pretend they're not there for just a minute. I know chemistry people are probably cringing, but it's okay. Calm down, glass of wine, something fancy with a duck on the box, maybe. So, lithium, 2 shells. Sodium, 3 shells, 1 in the outermost shell. So how it works is 3 shells, and then how many electrons can be in that shell is how many things are in the row. So the first row of elements, you have 1, 2 things in the row. That means the maximum number of electrons is 2. Here we have 1, 2, 3, 4, 5, 6, 7, 8. So the maximum number of electrons in that row is 8. Here we have 1, 2, 3, 4, 5, 6, 7, 8. The maximum number of electrons you can have in the third shell is 8, and then it progresses down. 8, 8. It changes just a bit because we do have this additional orbital that we're adding in, but like I said, for the purposes of anatomy and physiology, it's not relevant. So, what we need to know now is how do these things behave, because they're neutrally charged, yes, but in reality, if they were all neutrally charged, it just wouldn't be as much fun. So the first thing you need to realize is every element that we have, first of all, wants to be like this row right over here. It wants to be like that column. It wants to be a noble gas. The noble gases are special because their outermost shell of electrons is always full. Helium always has 2. Neon always has 8 in its outside shell. Argon has 8. Krypton has 8. Xenon has 8. Radon has 8. The kind of cool thing is when they first developed the periodic table, Gregor Mendeleev first created it. When he did, the noble gases weren't even present because he organized the periodic table based on reactivity. And based on reactivity, the noble gases are completely non-reactive. If you're one of the students that I see in class, effectively, I've told you many, many times about the Hindenburg. If you're not sure what the Hindenburg is, it was a blimp. It wasn't actually called a blimp. It was called a dirigible, maybe. But either way, it was back in the early 1900s, and they filled it up with hydrogen. They were big balloons that were filled up with hydrogen, and these balloons that were filled up with hydrogen were meant to be lighter than air because the vast majority of air is nitrogen. So it carried a lot of weight. It was able to be very, very buoyant. But the problem is hydrogen is super, super reactive because it is dying to be like helium over here. How this is particularly relevant is since hydrogen is dying to be like helium, it is dying to give up or accept an electron. With it being dying to give up or accept an electron, it makes so it reacts with sparks, it lights on fire, which is not really good if you're floating, several hundred feet above the air in a blimp filled with this. So if you look at videos of the Hindenburg, the entire thing went up in smoke, and it burned before it hit the ground, and most, if not all, the people on it died. And the catch is, it burned entirely within about 3 minutes. And so the problem they had was they threw the rope down from the actual blimp to the ground to release the static electricity that was accumulated in the blimp while it was floating through the clouds. When they did this, there was a spark that was given off between the rope and the ground. This spark lit the hydrogen, and the hydrogen lit on fire. So it was just a horrible accident, and that's the reason now that if you see the Goodyear blimp, if you think of when the last time you heard of the Goodyear blimp catching on fire, well, I haven't ever, because now blimps are filled with helium, and helium, as you can see over here, is completely non-reactive. It would be the same thing as if they would fill it with neon, or argon, or krypton, or xenon. The reason they picked helium as opposed to one of the other ones is because they want it to be lighter than air. Since the majority of the components of air are nitrogen, it has to be something that's lighter, has a lower mass. There we go. Nitrogen that we were talking about, the molecular mass is 14.007. We need something with a mass lower than that, but stable. Helium is the only thing that fits into that category. So it's really cool when you look at it from that perspective. This is also the reason that if you were to take a balloon filled with hydrogen and breathe it in, you probably wouldn't live to watch this video again. But if you take a balloon filled with helium and breathe it in, you're going to talk really funny, and assuming you don't do that for a prolonged period, then you'll be okay. It's not good to do that for a prolonged period because there is no oxygen in that balloon. So this is my little disclaimer. Don't breathe helium. It's a bummer. But helium is super stable, and that's the reason that medically we do use helium for patients on a regular basis. It's used for airway obstructions and things like that. So, just to give you an idea, I want you to kind of sit back and think about the fact that elements as they sit are neutrally charged. So, hydrogen is neutrally charged. Lithium, neutrally charged. Sodium, neutrally charged. So, lithium has 3 protons, it has 3 electrons. Beryllium has 4 protons, 4 electrons. Sodium, 11 electrons, 11 protons. Magnesium, 12 protons, 12 electrons. But the problem that these guys have is lithium, beryllium, magnesium, sodium, potassium, calcium, all these guys are super, super reactive because they want to have a full outside shell of electrons. Right now, lithium has 1 electron in its outside shell. It wants to give up that 1. Beryllium wants to give up 2 of them because it has 2 in its outside shell. So, how I often tell people to consider electron or atoms and whether they're going to give up or accept electrons is they're lazy. So, lithium, in this shell right here, this shell can hold a maximum of 8. Lithium has 1. So if you were lazy, would you be more likely to give up 1 or accept 7? Well, give up 1. So if you give up 1, you're giving up a negative charge because you're giving up an electron. When you give up a negative charge or an electron, you will then have, it's like losing a bill. So since you have the 3 protons that are present, and now you're losing an electron, so now you only have 2 electrons present. 3 is positive, 2 is negative. You wind up with a net of positive 1. So the net of positive 1, that means that lithium is a positive ion, Li plus 1. We can do the same thing for magnesium. Magnesium has 3 electron shells, 1, 2, 3. In its outside shell, there are 1, 2. But magnesium, as it sits, is neutrally charged. There are, as it currently sits, there are 12 protons and 12 electrons. Makes sense it's neutrally charged, there's 12 of each. Since this is positively charged, this is negatively charged, the sum of both of these is 0. Okay, that works out well. But magnesium, since it wants to have the same electron structure as helium, neon, argon, all these guys over here, right now it has 2 in its outside shell. This shell can hold 8. Is it more likely to lose 2 or gain 6? Well, it's lazy. It's going to lose 2. So when it loses 2, you still have 12 protons, but now we only have 10 electrons. So when we have 12 protons and go down to 10 electrons, it's going to leave us with a net charge of 2 plus. So magnesium, in the state that you're actually going to find it in, the stable state in your body, is going to be Mg2+. You don't find a whole lot of magnesium in your body. You do find some, and it is important for metabolic functions. But effectively, you don't tend to find a whole lot. But it does come into play when you start looking at how things bond together and what tends to bond with what. Now, I get a lot of questions from people about covalent bonding versus ionic bonding, and how can I tell, and which one is which. So this, unfortunately, because I'm trying to, kind of make this at the last minute for people, is going to be where I freehand draw, which is just altogether upsetting if you've ever seen my freehand drawing. But it'll be okay, I promise. So when you look, there's 2 primary differences. I'll draw 2 columns over here. We have covalent bonding, and then we have ionic bonding. So when we look, there are similarities between both of these, but there's also vast differences. So covalent bonding is bonding that occurs due to a sharing of electrons. Ionic bonding is a bonding that occurs because of different or opposite charges. Just a couple of common examples, and in the urine physiology lab, this does come up really regularly. Whenever you share electrons, this is where your outside shell is not full, and so the electrons are being shared between two different elements. The most common thing that we use in the urine physiology lab is glucose. That has an electron that has a chemical formula of C6H12O6. How this is particularly relevant is when you take glucose, throw it into water, it's not going to dissociate into anything else. It's still going to be C6H12O6. However, with ionic bonding, you have different charges. If we go back to the periodic table that we had, if we go back to the periodic table that we had earlier, and you look at two of the more common things. Sorry. This down just a little bit. There we go. This is perfect right here. So, and you go back, we look at sodium and chlorine. And sodium and chlorine together, sodium chloride, that's table salt. So whenever you have sodium chloride, we have the sodium that's present right here, and the chloride, or the chlorine, that's present right there. So effectively what happens is the sodium, in its normal, natural, relaxed, neutrally charged state, has 11 protons. So this is sodium. It has 11 protons and 11 electrons. The problem that comes in is sodium wants to lose one electron because it wants this outside shell to be full. What's it more likely to do? Gain 7 or lose 1, it'll lose 1. So, after that, it will be left with 11 protons, and the number of electrons will go down to 10, which means that sodium, in its neutral state, will have a charge of Na plus 1, or also written as Na plus. Chlorine, on the other hand, so we'll do Cl over here on this side. Chlorine, in its outside shell, has 1, 2, 3, 4, 5, 6, 7. What's it more likely to do since it has 7 and it can hold 8? Is it more likely to give up 7 or take 1? Well, it's more likely to take 1 because that's the lowest number. It's easiest to do. But in its neutral state, it has 17 protons, 17 electrons, which is 0. Everything's fine. But in its state that you'll find actually floating around in your body, you still have the 17 protons, but now you'll gain 1 electron, so you have 18 electrons, making it so the overall charge is -1. So that means that chlorine has a negative charge. Well, notice that Na plus and Cl minus have two different charges. So with the two different charges, they attract each other because, Paula Abdul says opposites attract. And, if you're sitting at home singing that song to yourself, then, you were around in the 80s. And a lot of the students I get have never even heard of Paula Abdul, so it pains my heart. But if you're singing that song to yourself, then cool for you. So this is particularly important because a covalent bond is physically stronger than an ionic bond. So whenever you toss glucose into water, the glucose, the carbon, hydrogen, and oxygen will continue to stay together. But whenever you toss sodium and chlorine, or sodium chloride or salt into water, what will happen is, because water is polar, and that's a whole other thing that we can get into later, but since water is polar, the polar portion of the water will attract, one portion will attract the sodium, the other portion will attract the chlorine, and the salt will break apart. So once you put salt in water, it no longer continues to be salt. It starts being sodium ions and chlorine ions. The question that I get from people on a fairly regular basis is, but I've poured salt into a glass of water, and when I pour salt into a glass of water, whenever I pour enough of it, I notice that the salt begins to just settle to the bottom. So doesn't this go against the fact that all the salt will dissociate? Well, there will come a point in a solution where you fill it with solute so much that all of the points on the water molecule, the polar water molecule, to bond with the sodium and the chlorine ions will fill. When this happens, there's nothing left to react with the water. So all the water's bonding spots are taken up. And when this happens, you form a precipitate. Precipitate is just undiluted or undissociated solvent, or solute, I'm sorry. But if you were to add more water, you would add more polar water molecules to make it so the salt that is undissociated would then dissociate. And this process is irreversible. Once it's done, it's done. So that's enough for this first little mini lecture. So look over this. If you guys have any questions, put them in the comments or shoot me an email. I've got another couple of them that are coming up pertaining to spontaneous ionization and then molar masses, molarity, osmolarity, that kind of thing. So let me know if you have any questions, and thank you very much.